Alright, I think we should be online now. Let me go ahead and see if I can see my hand and if I can hear myself. Okay, all sounds good. Then we are good to go. So I think I have a rough idea of what I want to do. Let me put the headphones away first. Alright, so since the last stream, which was about 2 hours ago, I was able to figure out finally what I want to do for this week. And it's just going to be a mixed review of mechanics topics. I'm just going to go through my book and pick out some problems that stand out, and we'll just do those, and that'll be that. There's not much point in starting calculus coverage now, what with the AP Calculus exam being 2 days away. Well, I guess 3, depending on how you count. But yeah, it's already too late for calculus this year, so might as well commit to physics. Oh, and before I begin, for whoever was here last week and the week before and heard all of those sound issues. So I did look back through the recording from last time, and I did determine that one of the sounds is really just me putting my hand on my desk. I guess the sound just kind of travels through the desk and reaches my microphone that way. So that's one of the sounds resolved. And as for that other knocking sound, my best guess, I'm pretty confident about this, is my chair. Sometimes when I lean back a little too hard on it, it makes this sort of snapping or knocking sound. So I think that's what the microphone is picking up. But the way it sounds when I listen to it in the video, it sounds almost like I'm tapping one of my markers against the table, like that. So that's why I didn't really recognize it. I guess when it gets filtered through the microphone, it just loses some sort of quality to it that would allow me to distinguish it from, well, that's not the right choice of words, but in the recording, it's hard to recognize it. It's hard to identify it as the sound of my chair. But yeah, I think that mystery is solved, so I'm going to try and avoid leaning back too hard against my chair, and I'll look through the recording this time and see if that knocking sound is not there. Or if I do end up leaning back too hard against my chair, I'll just call it out so that post-recording me will know that that was when it happened and can confirm for sure that that was the source of the sound. Come to think of it, what I should probably do is, outside of a stream, just do a quick sound-only recording and then play it back and see what it sounds like. That I should have come up with that idea days ago. I don't know why it's just now. Well, probably because I haven't been thinking about it much since reviewing the footage from last week. Anyway, let's go ahead and pick some problems here and get started. So I do have a few from previous recording sessions that I wish we could have gotten to that we never did. We'll start off with rotational dynamics. Rotational dynamics. There was one really good problem there that I liked. Here it is, number 55. Number 55. So it says, a cylinder with moment of inertia I1 rotates with angular velocity omega 0 about a frictionless vertical axle. So they have the axle, and then they have some sort of disk like so, and it's rotating with angular velocity omega 0, and it has a moment of inertia I1. And it has a moment of inertia I1. A second cylinder, or disk, with moment of inertia I2, initially not rotating, drops onto the first cylinder. Since the surfaces are rough, the two cylinders eventually reach the same angular speed omega. Calculate omega and show that kinetic energy is lost in this situation, and calculate the ratio of the final to the initial kinetic energy. So this is the before picture, and they drop a second disk on top. And the after picture, I think I'm going to draw the disks first. So there's disk 1. Something like that. And then disk 2, I probably should have drawn disk 2 first. Now my layers are going to be all messed up. I did not plan well for this. Yeah, that's what it should look like, and then we're going to have an axis of rotation, something like that. And it's now spinning as a system of two disks with a new angular speed, omega, not the same as the omega 0 that we started with. Maybe if I shade this, yeah, I think that helps make it a little bit more, I don't know what word I'm looking for here, a little bit easier to understand the drawing. Okay, so that second cylinder has a moment of inertia I2, so I guess I'll draw an arrow pointing to it. And that has moment of inertia I2, while this one still has moment of inertia I1. Determine omega and show that the kinetic energy is lost, and find the ratio of kinetic energy after to kinetic energy before. So we weren't given any numbers to work with, so this is what I like to call an expression problem. We're just solving for an expression. So we can just apply conservation of angular momentum here. Net torque on the two disks should be 0. Net external torque, I should say, is 0. There is a torque that is exerted on the disks, and that's the torque due to the friction that they exert on each other, but that is an internal torque since they're torques caused by the objects in the system on the objects in the system. So net torque external equals 0, which therefore means that angular momentum is conserved. That is, I initial omega initial equals I final omega final. So initially we just have I1 times omega 0. No angular momentum for the disk that's dropped on top of it. And then after, you've got the new moment of inertia is I1 plus I2 times omega final. They just called it omega. And pretty easy, just divide both sides. And we get omega is equal to I1 over I1 plus I2 times omega 0. A little bit sloppy with the way I placed it. Probably should have written it further to the left so that it would neatly fit behind that equal sign, but that's what it's supposed to be. So that's part A. And then for part B, show that kinetic energy is lost in this situation and calculate the ratio of the final to the initial kinetic energy. Okay, showing kinetic energy is lost means we need to show, actually let me do it up here. We need to show not SCO, I don't know why I tried to write a K there, show kinetic energy final less than kinetic energy initial. And we also need to find final over initial. Find kinetic energy final over kinetic energy initial. Okay. Showing that kinetic energy is lost shouldn't be too bad. Just follow this, and we need to prove that inequality. So kinetic energy final is 1/2 I final times omega final squared. And we need to show, is this less than kinetic energy initial 1/2 I initial omega initial squared. We can cancel the 1/2 on both sides. That's not going to matter. I final is going to be I1 plus I2. Omega final squared. Omega final is just that expression that we got earlier. Is I initial, or I1 I should say, over I1 plus I2 times omega 0. And then that whole expression squared. Is it less than I initial omega initial squared? That would be I1 times omega 0 squared. Okay, so we can see fairly clearly that the omega zeros are going to cancel out. This omega 0 is going to get squared, so omega 0 squared here cancels with omega 0 squared there. What else can we do? Well, let's go ahead and expand this a little. So this is going to become I1 squared over I1 plus I2 squared. I1 plus I2 squared in the denominator cancels with one set of I1 plus I2 over here. So that would just leave me with I1 plus I2 not squared in the denominator. I'll write it out instead of doing it all in one step. I1 plus I2 times, that becomes I1 squared over I1 plus I2 squared. We can cancel that. And then is that less than I1? We can divide both sides by an I1, leaving just 1 over here. And then what I can do is I can multiply both sides by I1 plus I2. So that leaves us with I1 less than I1 plus I2, which is pretty obviously true, but we can prove beyond a shadow of a doubt that it's true because we can subtract I1 on both sides, leaving 0 less than I2, which is most definitely true. If I2 is greater than 0, then I1 plus I2 is greater than I1, which means I1 is greater than this whole mess, which means then that I1 omega 0 squared is greater than this whole mess, which therefore means that this inequality is true, which means kinetic energy initial is greater than kinetic energy final. So yes, we have proven it. And for those of you worried about cases where maybe the inequality should have gotten flipped, none of the numbers we multiplied or divided by here would need to have negative values. There is no reason for any of our quantities here to be negative. The omega that we were given is angular speed, not angular velocity, so we don't have to worry about it being in the negative direction, however you define negative for this problem. It's magnitude only, and moment of inertia most certainly can't be negative, so yeah, we didn't have to flip our inequality symbol at any of our steps in case you were worried about that. Okay, and finally calculate the ratio of kinetic energy final to initial. Let's go ahead and see what I want to do for that. So I imagine I'll be repeating a lot of the steps that I did here. Let me take a look. So the 1/2 will cancel out, and the omega zeros will cancel out. At that point, I haven't moved anything to the left or to the right. I'm just doing multiplications and divisions, so that's fine. And over here, that's still dividing, so kinetic energy final over kinetic energy initial is simply 1 over this, which is, wait a minute, that can't be right. That would make it I1 plus I2 over I1. Okay, I guess I'm going to redo it from the start and see what I can find. So kinetic energy final over initial. So 1/2 I1 plus I2 times I1 over I1 plus I2 omega 0 squared divided by kinetic energy initial is just 1/2 I1 omega 0 squared. The 1/2s cancel out, omega 0 squared cancels out. I1 plus I2 cancels with 1 power of I1 plus I2, because this is just going to be I1 plus I2 squared, kind of like what we had over here. So I'd be left with I1 squared over a single I1 plus I2, and then that over a single I1. Okay, so it's just I1 over I1 plus I2. What did I do wrong? What did I do wrong over here? Oh, I know. I misread. This is the initial kinetic energy side. This is the initial side. I mistook it for the final, which is why I ended up thinking it would be I1 plus I2 over I1. Yeah, I had it backwards. Okay, I see that now. So kinetic energy final over kinetic energy initial. I guess I'll write it in another color over here and over here off to the side. So I'll take this and sneak it in here. Kinetic energy final over initial is equal to I1 over I1 plus I2. The fraction of the total moment of inertia that is taken by the initial disk. All right, that takes care of that one. Now let me look through here and see what else there is to find. I think I had one for simple harmonic motion that I wanted to do, but I'm not entirely sure. Yeah, this one is going to be kind of freestyle compared to previous office hours sessions. And then I am most likely going to be doing some math next time. No, that one's a fairly standard problem. Okay, I guess I got my hopes up for nothing. Either I'm thinking of a completely different problem, or the problem that I'm looking at is not the difficulty that I remember it being. Okay, I'll go back. So Another problem that caught my eye while I was flipping through this book was a momentum problem. Here we go. It says, a cannon is rigidly attached to a carriage which can move along horizontal rails, but is connected to a post by a large spring, initially unstretched, and with force constant K equals 2 times 10 to the 4 newtons per meter, so 20,000 newtons per meter. The cannon fires a 200 kilogram projectile at a velocity of 125 meters per second, directed 45 degrees above the horizontal. If the mass of the cannon and its carriage is 5,000 kilograms, find the recoil speed of the cannon. Determine the maximum extension of the spring. Find the maximum force the spring exerts on the carriage, and consider the system consisting of the cannon, the carriage, and the shell. Is the momentum of this system conserved during the firing? Why or why not? So that's a lot to take in. Let me draw the diagram first so that all this talk about cannons and carriages actually makes sense. And then we'll get on with the actual problem. So they have a floor and a wall, and attached to that wall is a spring. And connected to that spring is a sort of cart, or what they called a carriage, with wheels. And on this carriage there is a cannon. Probably not the best cannon I've ever drawn, but it'll have to do. And from this cannon, which is angled at 45 degrees, by the way, 45 degrees, I don't even know if that's readable. Good enough. And this thing fires off a projectile. So let's read again. The spring constant was given as 20,000 newtons per meter. The cannon fired a 200 kilogram projectile, so I guess I'll call it M proj. Mass of the projectile is 200 kilograms. Initial velocity of the projectile is 125 meters per second. I'll call that V projectile. V projectile. 125 meters per second. 125 meters per second at 45 degrees to the horizontal. And they say the mass of the cannon and its carriage is 5,000 kilograms. So mass, I'll just call it M cannon. Is equal to 5,000 kilograms, including the apparatus upon which it sits. Find the recoil speed of the cannon. So find V cannon. This is immediately after the launch of the cannonball, or projectile as I called it in my variables. That is what we need to find. Okay, so we can apply conservation of momentum here because the only forces, this is before the spring gets stretched out. We're just talking about immediately after the cannonball is fired. So the spring force does not influence the calculation that we're doing right now. We can say in that moment of the projectile being fired from the cannon that the only forces acting are the cannon on the projectile and the projectile's reaction onto the cannon. Those are internal forces. All other forces will net out to 0 in that moment. Is that actually an accurate statement? Well, if we want to be super technical about it, gravity does have an influence, but assuming that this happens in a very, very short amount of time, assuming this happens instantaneously, there's not enough time for gravity to influence the momentum of the cannon or the projectile fired from the cannon. So we can still argue that momentum is conserved. Even if we did want to take gravity into account, it would only have an effect on the vertical momentum and not the horizontal. So horizontally, at the very least, momentum is conserved. Net force external in the x direction, at the very least, is 0 in that moment. Although it won't be for long, because once that cannon gets pushed back by recoil, the spring is going to start kicking in. So then we can do, at least in the x direction, m projectile times v projectile in the x direction initial plus, actually, I'm going to say final, plus m cannon, not camm, m cannon times v cannon in the x direction, final, is equal to what were the x components of the velocities of the cannon and projectile before firing? 0. So there was no initial momentum. Okay. So then v cannon in the x direction is simply going to be, subtract this term over to the right hand side and divide by the mass of the cannon. So we will have v, I guess I'll just call it v cannon x, no need to also specify that it's final, is equal to negative mass of the projectile is 200 kilograms times v of the projectile in the x direction is going to be 125 times cosine of 45 degrees Divided by the mass of the cannon and its carriage, which is 5,000 kilograms. Okay, we can plug all that in. And let's see what it gets us. 200 times 125 cosine of 45. Is my calculator in degree mode? Yes, it is. That's something I have to check for more often these days because I have had to switch back and forth between degrees and radians recently. And then that divided by 5,000. And I'm getting 3.535533. That's a lot of 5s and 3s. And then it ends with a 906 and breaks the pattern. I'm just going to round it to 3.536. Negative 3.536 meters per second. The negative just means that it'll be to the left, assuming positive is to the right. So you can actually drop the negative and just call it 3.536 left instead. That's part A. Part B, determine the maximum extension of the spring. Determine the maximum extension of the spring. So this, I guess I shouldn't have even called it final velocity here because it's not really final. It's just the velocity after the moment of firing. But there are still more changes to come. So this is actually, you could consider it the initial velocity for this next part of the problem. So for the next part of the problem, we can say that conservation of energy applies between the cannon and its carriage and the spring. We can say that the energy in that system is conserved because there won't be any, let's see, normal force is going to act vertically, so it does zero work for a cannon and carriage that's going to move horizontally. Force of gravity, for similar reasons, is going to do no work, but even if it did do work, it would be conservative work. So energy would have still been conserved in that case anyway. Friction is not going to do any work on the wheels, assuming the wheels roll without slipping, which is a reasonable assumption. Otherwise, they would have told us that friction does some work. So we can assume that friction between wheels and the floor is negligible. So yeah, that only leaves the spring force, which is a conservative force. So non-conservative work is zero, therefore mechanical energy change is also zero, which means mechanical energy final equals mechanical energy initial. Mechanical energy initial, I say initial in quotes because it's not the first thing that happened, it's actually the second thing if you count the firing of the cannonball as the first event. But in any case, let's not split hairs over that. If we start with the cannon recoiling, that's going to be 1/2 mv squared for the cannon. 1/2 mass of the cannon and its carriage is 5,000 times the speed is going to be 3.536 squared. So that's the kinetic energy, and there's no potential energy for this cannon and carriage in that initial moment, and that's going to equal when the cannon and carriage stretch as far as the spring will let them go, they'll be at zero velocity, so there will be no kinetic energy left. All the remaining energy is going to be potential energy, so 1/2 kx squared, that's 1/2 times 20,000 for the spring constant, times x squared. Solve for x. We can cancel the 1/2, which is nice. It saves us a little bit of time. A few less buttons to press on our calculator. And actually we can cancel 1,000 on both sides as well. So 5/20 times 3.536 squared. 5/20 times 3.536 squared gets me 3.125824. That should be equal to x squared. If I take the square root of that, I get 1.768. I get x is approximately 1.768 meters. And there's part B. Part C, find the maximum force the spring exerts on the carriage. Okay, that's actually pretty easy now that we've done the previous part. The maximum force would be at the maximum stretch. The spring force, at least the magnitude of it, is equal to the spring constant times the stretching distance. So the maximum force occurs at maximum stretch, and we just said the farthest the spring will stretch is 1.768 meters. So just plug in 20,000 times 1.768 or 20 times 1768, and that's 35,360 newtons. 35,360 newtons. And that takes care of part C of that problem. Part D, consider the system consisting of the cannon, the carriage, and I guess they called it the shell. Is the momentum of this system conserved during the firing? Why or why not? Let's see, if we consider the cannon, the carriage, and the shell. Okay, well, the cannon and carriage, we've been treating them as a single object anyway, of mass 5,000 kilograms, and the shell is just the cannonball. So we did say that the momentum was conserved, but only in the x direction. The momentum is conserved in the x direction, but the overall momentum in 2 dimensions is most certainly not, because launching a cannonball, or as they called it, a shell, at an upward angle would imply that you're giving this shell some upward momentum, and for the vertical momentum to be conserved, you would need the cannon and carriage to have a downward momentum after firing off the shell. And clearly that's not the case, and that's because there's an external force, namely normal force, that prevents that from happening. Normal force adds some vertical momentum to the cannon and carriage, just enough to cancel out any negative vertical momentum they would have gained from firing the projectile. So if we are being completely honest with ourselves, momentum overall is not conserved. It's only conserved in the x direction, and only for a brief moment, because once that cannon is in the air, the spring starts to also influence the... Did I say cannon? I meant cannonball. Once that cannonball is in the air, the spring starts to alter the momentum of the cannon and carriage. So that takes care of part D, and that's the end of that problem. Alright, let me look and see what else might be of interest. I feel like there was a good kinematics problem in here somewhere, although I guess the AP Physics students don't need much of that, so that might not be the best thing to prioritize. I wish I had decided what I wanted to do for this session earlier. Then maybe I would have had more time to actually pick out problems instead of being stuck having these long, awkward pauses while I look for problems. Okay, this one is a good one. My students have seen this one before, but it doesn't hurt to review. There's a reason that I make sure students see this one. So it's a kinematics problem. It says an ice sled powered by a rocket engine starts from rest on a large frozen lake and accelerates at 40 feet per second squared. After some time t1, the rocket engine is shut down and the sled moves with constant velocity v for a time t2. If the total distance traveled by the sled is 17,500 feet and the total time is 90 seconds, find the times t1 and t2 and the velocity v. Then, at the 17,500 foot mark, the sled begins to accelerate at negative 20 feet per second squared. What is the final position of the sled when it comes to rest? And finally, how long does it take to come to rest? So we've got 3 different phases to this problem. So what I like to do here is put together 3 whole sets of kinematic variables. Oh goodness, I'm having trouble getting this straightened out on my screen. I know that can bother people. Okay. So we have, I guess I'm going to call them V0, V1, A1, t1 and delta x1. And then we've got, in the second phase, we'll start at v1, end at v2, which are actually going to be the same because the second phase is a constant velocity phase. a2, t2, and delta x2. And phase 3 starts at v2, ends with v3, add acceleration a3 for a time t3 with a displacement delta x3. All right, let's fill in the information we know. So I'm going to read the problem again for those of you who didn't catch it all when I read it the first time. So it says an ice sled powered by a rocket engine starts from rest, v0 equals 0, on a large frozen lake and accelerates at 40 feet per second squared. 40 feet per second squared. We actually will not need to convert to meters here because everything else is also reported in feet, so the units will work out just fine. After some time t1, the rocket engine is shut down and the sled moves with constant velocity v for time t2. Constant velocity, they just called it v for a time t2, and they said it was constant, so in the second phase the acceleration is 0, which means v2 is also equal to whatever this v is. And then they say if the total distance traveled by the sled is 17,500 feet and the total time is 90 seconds, find the times t1 and t2 and the velocity v. So that's the first half of the problem. So they say the total distance, which we can assume is the total displacement. We can assume that the sled only moved in a single direction, and if an object only moves in one direction and never turns around, then distance has the same magnitude as displacement. So total distance for those first two phases is equal to total displacement magnitude delta x1 plus delta x2 equals 17,500 feet, they said. They also said that these first two phases take 90 seconds. t1 plus t2 equals 90 seconds. And they want us to find the times t1 and t2 and the velocity v. Okay, so I can just use these two equations together. I need to rewrite one of them because right now I've got two equations with 4 unknowns. I'd like to simplify that to two equations with 2 unknowns. And there is a convenient way to do that. Well, actually I might need 3 equations here looking at it, but let's figure out what we can figure out before I make any other statements. Let's see what we have to work with. So I can write the delta x's in terms of t by using the second equation of kinematics. I can say delta x in general is equal to v initial times t plus 1/2 the acceleration times t squared. So I can do delta x1 is equal to v initial for phase 1 is 0 times t, so 0, plus 1/2 the acceleration, that's 1/2 of 40, which is 20. times t squared, in this case the t being t1 squared. Okay, delta x2 on the other hand is going to be, well, it's going to be v times t, the t being t2 and the v being v1, which is equal to the unknown velocity v that they want us to find, plus 1/2 the acceleration times time squared. Acceleration for phase 2 is 0, so that's all just going to be 0. Okay, so I still have my unknown v, but let me go ahead and rewrite what I currently have. So I've got delta x1, which is 20 t1 squared, plus delta x2, which is vt2, equals 17,500. Okay, so now I've got 2 equations and 3 unknowns. Let's find a relationship between v and at least one of those 2 t's. I think I can just use the first kinematics equation there, so if I do v final equals v initial plus at, if I use that in the first phase, then I can get v final, which is v1 in that case, which is v, equals v initial, which is v0, which is 0, plus the acceleration, which is a1, that's 40, and then t, which is t1 for the first phase. Okay, there we go. So that gives me 20 t1 squared plus vt2, v being equal to 40 t1, so 40 t1 t2, and that equals 17,500. All right, so far so good. Now I want to take this and this together to solve for t1 and t2. So, best option here that we have is substitution, although it can get quite ugly. Best option we have is substitution. So I'm going to do t1. Well, actually I think I want to substitute for t2. That way I only have to plug in one place instead of 2. Yeah, I'll solve for t2. t2 is equal to 90 minus t1, and I'll plug that in here. So we get 20 t1 squared plus 40 t1 times t2, again, is equal to 90 minus t1, and that equals 17,500. I think I want to reduce everything by 20 just to make the math a little easier, so let's go ahead and do that. t1 squared plus, that'll be 2 t1 times 90 minus t1 equals, what's 17,500 over 20? Well, that would be 1750 over 2, which is, let's see, 800 plus 50 plus 25, 875. Okay, and if I distribute 2t1 over 90 minus t1, then I get t1 squared plus 180 t1 minus 2 t1 squared equals 875. t1 squared minus 2 t1 squared is negative t1 squared. And I'm going to take all this and move it to the right-hand side. So I guess I'll continue this up here because I planned poorly with my spacing. So I'll be left with 0 on the right-hand side equals, let's see, negative t1 squared adds to the right and just becomes positive t1 squared minus 180 t1 and plus 875, since the 875 never had to be moved, it was positive to begin with. Okay, and this right here is a quadratic. Let's see, can we factor it? Oh boy, 875. Well, how many 25s are in there? So there's 4 for every 100, so 4 times, we've got 800, so that's 32. And then we've got 3 more 25s for the 75, so that's 35. Right? 35 times 25. Do I have that right? 32 of them gives me 800 plus 3 more gives me 75. Yeah. So this is 35 times 25, and we could probably factor it further than that. 35 times 25, or 7 times 5 times 5 times 5. I don't see that adding up to 180, so I think I'm just going to resort to the quadratic formula after all. Okay, so t1 equals negative b, so 180, plus or minus the square root of b squared minus 4ac. Negative 180 squared is the same as positive 180 squared, so I'll skip on writing the negative. Minus 4 times 1 times positive 875 all over 2a all over 2 times 1. Okay, if I put that into my calculator, what are the two options that I get? So first I'm going to try plus the square root, so 180 plus square root of 180 squared minus 4 times 1 times 875 all over 2. That gives me 175, and if I do minus the square root, I get 5. So 175 and 5. I guess it could have been done by hand, but not very easily. Not very easily. So T1 equals 175, or T1 equals 5. A lot of times when you have to use the quadratic formula for kinematics problems, one of the time options is positive and the other one is negative, and then you know to just ignore the negative one. But this time, both of your options are positive, so what gives? How do we know which one is valid, or are they both valid? That is the importance of this question right here. T1 equals 5 is the only correct one. What's the problem with T1 equals 175? You might want to pause the video if you're watching this in video form to think about it for a few minutes or seconds, depending on how quickly you can realize what's up. T1 equals 175 does not make sense here because that would mean 175 plus T2 would have to add up to 90 seconds. That would mean that T2 has to be negative, which wouldn't make sense. We usually don't work with negative time. I mean, if you do the math, mathematically, there's nothing wrong with negative time, but the physical interpretation of negative time just doesn't make sense for our problem. We could construct a problem where negative time made sense if an object was already moving before we started the stopwatch, and then we start the stopwatch in the middle of its motion and do something like calculate its position before we started the stopwatch, then negative time would make sense in a scenario like that. But over here, T2 being negative wouldn't make sense. So T1 equals 175 seconds is not valid. Okay, so T1 equals 5 seconds. T1 equals 5 seconds, which then means that T2 has to be 85 seconds. And that takes care of the first part. Find the velocity v. Well, now that we know what T1 and T2 are, we can just say, where did my equation for v go? There it is. V is equal to 0 plus 40 times T1, so 40 times 5 seconds would be 200. So V is equal to 200, and that's going to be in units of feet per second. 40 times 5, yeah, 200. So all of these are 200 in feet per second. Feet per second. Oh, and come to think of it, that V2 also carries over to here, 200 feet per second. And I didn't finish filling out this data, but I guess that's because I didn't get to reread the next half of the problem. So let's get to that. Now it says at the 17,500 foot mark, so after the first two phases of the motion, the sled begins to accelerate at negative 20 feet per second. So the third acceleration is negative 20 feet per, did I say second? Per second squared. Now it's asking, what is the final position of the sled when it comes to rest? For that, we would need to, well, actually, we only need delta x3, and then we can add it on to the 17,500 and be done with it. And then the last part is, how long does it take to come to rest? Well, if they're saying it comes to rest, then we know that V3 is 0. And with those three pieces of data, we can calculate the other two rather easily. With an acceleration of negative 20 feet per second squared, if you start at 200 feet per second, and every second you lose 20, then it will take 10 seconds to lose all 200. That's just the intuition of the first kinematics equation there. V final being 0 equals V initial is 200 minus 20 T3 minus 20 T3 is equal to, if I subtract V initial over to the left, it'll be negative 200. Negative 200 equals negative 20 T3. I guess I'll write it. So 0, 200, negative 20, and T3. Yeah, subtract 200 on both sides. You get negative 200 equals negative 20 T3. Divide by negative 20. The negatives cancel. 200 over 20 just reduces to 10. So T3 equals 10 seconds. I mean, it feels a bit small, but then again, if you were accelerating for only 5 seconds, then despite having the higher acceleration, yeah, I guess that makes sense. I don't know, it just felt a bit wrong there for a second. Okay, and then delta x3 is the last thing we need. So delta x3 is just going to be, I guess I'll just use do I want to use the third or the second? I guess I'll use the third since we haven't used it at all today. So v3 squared equals v2 squared plus 2 times a3 delta x3. So that's going to be 0 squared equals 200 squared. Is that even visible on the screen? Now it is. Plus 2 times negative 20 times delta x3. Okay, so 200 squared is going to be 40,000. Subtracted on both sides, you get negative 40,000, and 2 times negative 20 is negative 40, so you'll have negative 40,000 divided by negative 40 equals delta x3. Negative 40,000 over negative 40, the negatives cancel. 40,000 over 40 is just 1,000. So delta x3 is only 1,000 feet. Positive 1,000 feet, which means it's 1,000 feet forward from where it was at the beginning of phase 3. And at the beginning of phase 3, it was at 17,500 feet. So its final position would be 17,500 plus 1,000. X final would be at 18,500 feet. The way I circled over that X final is a bit sloppy, I know, but I can't really erase ink. Okay, that takes care of yet another problem. I could have sworn I had a really good one for simple harmonic motion, but oh well. Let me try looking for it one more time. If not, then maybe I can give the circular motion chapter a try. think I found a pretty decent one, not the one that I remember, but it might be good. Let me finish reading through it just to make sure. Okay, that part makes sense to me. Okay, let's actually do this one. This one seems interesting, and I'm not entirely sure I'll get it right on the first try. But that's what makes it a good problem. So it says an object of mass m1 equals 9 kilograms is in equilibrium while connected to a light spring of constant k equals 100 newtons per meter. I'm going to go ahead and draw what they have over here. They've drawn multiple phases, actually. And come to think of it, oh, yeah, I guess they did ask about that. I was about to say, they have something in their drawing that's labeled that wasn't really mentioned in the problem statement, but it actually is mentioned, just not directly. They just don't reference the way that they labeled it, at the very least. So we've got a wall. Actually, let me draw it over here. We've got a wall and a frictionless surface and a spring that is, well, they've drawn it initially unstretched, just at its natural length. With mass m1 attached to it. You can't even read that. It's supposed to say m1, but oh well. I can't wait for this yellow marker to die. I mean, I feel half tempted to just throw it in the trash right now, but that would be wasteful, and I'm not an advocate for wastefulness. Phase 2, they push a block against that first block. So now your M1 is over here, and it's got a second block pushed against it, M2. Probably not readable. I'll write over it in another color that's easier to read. Then this system is released from rest. And when it goes to the equilibrium position, M1 begins to separate from M2. And then M1 continues to the right for a while, but it's going to be slower than M2 because it's got the spring pulling back on it, slowing it down. and by the time that M1 reaches there, do I have enough space for it even? M2 is long gone and has separated by quite the distance, which they labeled as capital D over here. And let me rewrite all the written stuff so it's easier to read. M1, M1, M2, M1. That's not how the 1 is supposed to look. There we go. M2, M1, and M2, and D. There. That looks a lot better on my screen at the very least. Not sure how it's going to turn out in the video. You would think that an HD document camera would do better than this, but maybe I need to buy myself a new one. Either that or there's something about my physical setup that's wrong. I'll have to play around with that stuff if I can remember to do so. Anyway, now let's read the problem statement again. An object of mass m1 equals 9 kilograms, so let's write that down. I guess I'll write it over here. m1 equals 9 kilograms. Is in equilibrium while connected to a light spring of constant K equals 100 newtons per meter. K equals 100 newtons per meter. That is fastened to a wall as shown in the figure, which I already drew. A second object of mass m2 equals 7 kilograms is slowly pushed up against m1, compressing the spring by the amount A equals 0.2 meters. A equals 0.2 meters. That's how far m1 gets pushed. So that will be the distance A from equilibrium. The system is then released, causing both objects to start moving to the right on the frictionless surface. Part A says when m1 reaches the equilibrium point, m2 loses contact with m1 and moves to the right with velocity v. Determine the magnitude of v. So they're saying m2 is going to have some velocity v, and we need to determine what that velocity is. Then it says for part B, how far apart are the objects when the spring is fully stretched for the first time? And it has a hint. It says first determine the period of oscillation and the amplitude of the M1 spring system after M2 loses contact with M1. Okay, I'll keep that in mind. Oh, okay, yeah, I see. I see what they want us to do. I see exactly what they want us to do. So V is unknown, and D is also something we need to determine. So I'm going to do, let's see, to find V, well, we're going to have just conservation of energy for that is all we need to do. So all we need to do is say energy initial, which is just 1/2 K times the amplitude squared, equals the energy at this point when the two objects begin to separate, which is when you reach equilibrium. That's at x equals 0, so the spring potential energy is going to be 0 at that point, so it's all kinetic energy. So it's all 1/2 m1 v squared plus 1/2 m2 v squared. And they're both going to be moving with the same speed up until that point. So that's going to be the speed with which the second block will move for the rest of the problem. So yeah, these v's are actually equal at this moment. I can cancel the halves, which is great, less nasty fractions for us to work with. And I know m1 and I know m2 and I know k and I know a, so I can go ahead and plug in all that information and solve for v. So we've got k, which was 100, times a, which was 0.2, squared, equals m1 v squared plus m2 v squared is m1 plus m2 all times v squared, so that's going to be 9 plus 7 all times v squared. Okay, 100 times, that's going to become 0.04. 100 times 0.04 is just 4, equals 16v squared. Oh, they chose nice numbers for us. 4 over 16 is 1/4, equals v squared, which tells us then that v must be equal to 1/2 of a meter per second. And let me write that a little bit better. V equals 1/2 or 0.5 meters per second. Yeah. That looked too ugly for my tastes. Okay, so that's that part solved, and then it says how far apart are the objects when the spring is fully stretched for the first time? Okay, so when the spring is fully stretched, well, now we need to figure out how far from equilibrium will m1 go. Is it the same amplitude as before? I'm doubting that, so I need to figure out what this is. I need to figure out what this distance is. I guess I'll call it, what do I want to call it? I guess I'll call it a star. Let's see what we can do with it. So I can apply conservation of energy again. This time I'm going to say the kinetic energy that m1 had at this point equals the spring potential energy that the system will have at this point. So 1/2 m1 times v squared is equal to 1/2 k times a star squared. The 1/2s cancel out again, which is nice. m1 is 9 kilograms, and v squared was 1/4. Equals, let's see, k is 100, and that leaves us with a star squared we need to figure out still. So that's gonna be, if I divide by 100 on both sides, oh boy, 9 times 1/4 divided by 100 is 0.0225. Yeah, definitely not the same amplitude we had before. Not even close. And actually, the drawing in the book acknowledges that, which is nice. So, oh, wait. Actually, I'm not done yet. That's a star squared. So a star squared, glad I caught that in time, is equal to 0.0225, the square root of which I think is actually 0.15. Let's check. I knew it. It helps to know that 15 squared is 225. Reminds me of a moment when I was doing AP Physics in high school, and one of my classmates thought he would stump me by asking me what 1.4 squared is, and I said 1.96 immediately, and he had to plug it into the calculator to check, and his reaction was just, "Oh man." If you know a bunch of your perfect squares, then squaring with decimals isn't that much harder as long as you keep track of how many decimal places you end up with when you square. Basically, your decimal places will double whenever you square something. So, yeah. And I guess that would also mean that they get cut in half whenever you square root a decimal. So that's how I knew 4 decimal places would reduce to 2 decimal places. Just a fancy little math shortcut. You can probably convince yourself that it's true with a little bit of thought, but the point is, a lot of people don't take the time to put that little bit of thought into it, so they live out the rest of their lives never knowing this really simple trick. Anyway, we got a star is equal to 0.15, which is still less than the initial amplitude, but not by as much as I would have thought. Okay, so that's actually how far M1 continues to go by this point. That is important. We also need to calculate how far M2 travels in that same amount of time. And then we need to add those, or add or subtract. Well, we'll figure that out in a minute. So we need to figure out how long it took M1 to get here. And the hint pretty much spelled it out for us what we need to do. The hint says, I read it before, but I'll read it again. The hint says, first determine the period of oscillation and the amplitude of the M1 spring system after M2 loses contact with M1. Well, we already took care of the amplitude part. Now let's get the period, which is not related to the amplitude at all. Period for a mass spring system is I guess I'll write it up here. Let's wall some stuff off. I repeated it many, many times last week. Period for a spring is 2 pi square root m over k. 2 pi square root m over k. So, square root of, I guess it'll be 9 over 100 equals 2 pi square root of 9 over 100. Square root of 9 is 3, and square root of 100 is 10, so 3 over 10. 2 pi times 3 over 10, or 2 pi times 3 becomes 6 pi over 10. That's almost 2, but not quite. I guess we'll plug it in and see more precisely how much that is. 6 pi divided by 10, I'm getting 1.885 seconds equals approximately 1.884 0.5 seconds. All right. .885 seconds. That's the period for a full cycle. How much time does it take to get from the equilibrium position to the new amplitude? A full cycle would be from equilibrium to one of the amplitudes, then back to equilibrium, then to the other amplitude, and then back to equilibrium again. That's 4 different transitions. Equilibrium to one amplitude, back, equilibrium to the other amplitude, and back. That's 4 phases that are all symmetric, so the time it takes to get from equilibrium to the amplitude just once without going back and forth is 1/4 of the period. So we need to take time elapsed since M1 and M2 for that matter reached equilibrium for the first time is period over 4. Period over 4 equals T, I guess, since I don't even know what I want to call this. Let's call it T elapsed. Yeah, that's the best term I can come up with off the top of my head right now. Time elapsed since reaching equilibrium. So 1.885 over 4 is 0.47125. Okay. Equals 0.47125 seconds. Okay, and in 0.47125 seconds, how far does block M2 travel? So I guess I'm going to say delta x1, displacement of block 1, is 0.15 meters since the moment that the 2 blocks separated. What about delta x2? Delta x2, unlike delta x1, can just be calculated from a constant velocity relationship. They did say the table was frictionless. The only forces acting on block M2 then would be normal force and gravity, which cancel each other out. There is no net acceleration on block 2 until, I don't know, it falls off the table or something. So its velocity is constant, and if its velocity is constant, then we can just do velocity times time, and we don't have to add anything else to that. You would do v times t, v being, where was it? We calculated it earlier. 1/2 of a meter per second, so 0.5 meters per second, times t elapsed, which is 0.47125, plus 1/2 at squared. A is 0. No acceleration, so plus nothing. Okay, 0.5 times 0.47125 is 0.235625, which is a lot, so I'm going to round it. What do I want to round it to? I don't even know. You know what? I'll keep it as is. I don't know. Something about it looks nice enough that it would be a shame to round it. I know that's not really a good basis on which to decide whether or not a number should be rounded, but we're not worried about sig fig rules anyway here, so we can afford to be a little bit less nitpicky over how we round. Okay, and that is also in units of meters. Okay. So block 1 traveled this far. In the same amount of time, block 2 traveled this far. How far apart are they at that moment? We would just calculate the difference between these and we would have it. So delta x2 minus delta x1. Delta x2 minus delta x1 would equal our distance d over there. Equals 0.235625 minus 0.15. Okay, I think I'll round that final result. Minus 0.15 gives me 0.085625. I don't know, I don't feel like rounding that either. Okay, I'll keep it unrounded. 0.085625 meters. Well, that was fun. I could definitely see this being an AP exam problem one day. One day. We've got 15-ish minutes left on the clock. What can I do with 15 minutes? Let's see. We've done some rotational dynamics. We've done some kinematics. We've done simple harmonic motion. Let me see if there's anything interesting we can do with circular motion. I guess we could also just do a force problem. But I already have my my force review video, so I don't really think that I need to do any force problems, but let's look around in the circular motion chapter and see if there's anything worthwhile, whether it's circular motion or gravitation for that matter. I think this one, let's see. A skier starts at rest at the top of a large hemispherical hill. Neglecting friction, show that the skier will leave the hill and become airborne at a distance h equals radius over 3 below the top of the hill. And there's a hint that says at this point the normal force goes to 0. Okay, let's have a look at this one. So this one, I was asked a pretty much identical question. The scenario was different, but it was still the same frictionless hemispherical shape that we were dealing with. Actually, I think the question that I got from my student was somebody on the top of a sphere, but it doesn't really matter whether it's a sphere or a hemisphere. The end result is the same. So we have a skier who reaches a part of their ski slope that is in the shape of a hemisphere, like so, and I guess it eventually descends into like a regular hill. But this part of it, let me get these markers out of my way. This part of it is basically half of a sphere, or half of a circle if you're just looking at it from a 2D perspective. And I guess I'll draw the skier. I'm not sure how I'm going to draw the skis, but there's the skier, and we'll just pretend that that's a pair of skis. And I'm not going to draw the... I don't even know what you call the rods or sticks that skiers use. Just goes to show you how much I know about sports. Anyway, this hemisphere has some sort of radius r, and they are saying that the person falls off and becomes airborne at a distance h equals r over 3 below the top of the hill. So they're saying if the top of the hill is here, they're saying the point at which they fall off, this point, occurs after they drop by a height equal to r over 3. That's what they want us to prove. Prove that after this person drops r over 3 sliding along this hill, they will become airborne. They will lose contact with the hill and they'll just fly off like this. So they're gonna move, they're gonna be in contact, in contact, in contact, in contact, and then at this point here they're gonna fly off like this. And then they'll just engage in projectile motion rather than uniform circular motion. Okay, so there's a complicated way to do this and there's an uncomplicated way to do this. The complicated way to do this would be to use calculus. You'd have to, I guess, start with, you'd have to define an angle over here, and I guess you would set the angle to 0 over here and make the angle increase until you reach, what would it be? 30 degrees or maybe 60 degrees or maybe something in between. I don't even actually know. That might be worth looking into actually, but we'll figure that out later if we have the time left over. So that's one thing you could do. You could try to figure out how the angle varies with time, and you're going to have a variable speed at different points here, so you'd have to do an integral, and it can get really messy just setting it up. Forget about actually doing the calculus. Setting it up would be somewhat of a nightmare, but you can avoid all of that if you remember to just use conservation of energy to figure out what the speed is going to be over here. That's the key. So it's not entirely uniform circular motion that we have here. So we have accelerated circular motion because the force of gravity downward is going to be constant, but the normal force is going to vary. If not in magnitude, it's going to vary in direction, because at first the normal force is straight up, then it's going to be angled slightly, then angled more, and yeah, that affects things. So the person can actually still be accelerated downward by gravity, which means they are gaining speed as they go down this hill. If you don't have a constant speed, you don't really have uniform circular motion, now do you? So then, let me figure out what I want to write down. Let me reread the problem again. So a skier starts at rest at the top of the large hemispherical hill. That's good to know. So over here, up here, V equals 0. And yeah, I think from there we can get started. So I can apply conservation of energy because it did say we can neglect friction. And yeah, this is, we're talking about skiing over ice here, so friction is, you could assume, even if they didn't state it, unless they specifically said don't neglect friction, you could get away with just assuming it's not here. It's a pretty reasonable assumption. So then that means our energy is conserved because the only forces acting on the skier would be the force of gravity and the normal force. The normal force is perpendicular to the skier's motion at all points in time, and if your force is perpendicular to your motion, then the work done by that force is 0. So total non-conservative work is 0. I know people get annoyed that I take that step, but it's important. It's important to make sure that you actually know that mechanical energy is conserved and you don't just assume it just because. You need to be able to understand why mechanical energy is conserved. No friction isn't a sufficient condition for conservation of energy. There are other non-conservative forces aside from friction, and you need to account for why or why not they have an effect on your mechanical energy. Anyway, so change in mechanical energy is 0, which means mechanical energy initial equals mechanical energy final. So I'm going to say 1/2. Well, I guess, 1/2 m, I guess we'll call it V final squared, plus mg h final equals 0 initial kinetic energy plus mg h initial. The mass cancels out. Gh initial minus gh final, if this is h initial and this is h final, if this is h initial and this is h final, then h initial minus h final is just this h over here, which we haven't proven yet is r over 3, so we'll just call it h. So yeah, subtract gh final on both sides, and you get 1/2 v final squared equals just gh, h being equal to h initial minus h final. Multiply by 2, and you've got v final squared equals 2gh. Okay, I'm going to hold on to that. Now I want to apply some circular motion concepts. So if this person loses contact with the surface of the hill, then like they stated, that means that the normal force goes to 0 at that point. Normal force is a pretty good indicator of how strongly something is in contact with something else, if that makes any sense. If I press my hand against a wall, the normal force that my hand exerts on the wall, and by reaction, the normal force that the wall exerts against my hand, the harder I press my hand into the wall, the stronger that normal force is. If I just touch the wall, I give it a shallow touch, then I don't have any normal force between me and the wall. Similarly, I guess this one is actually a more intuitive one, is imagine if you had like ropes tied to the ceiling or maybe to like some sort of gym equipment or whatever, and you hold those ropes and you pull on them just strongly enough that your feet are still touching the ground, but you don't feel any of your weight on the ground. That is the moment that you're about to lose contact with the ground. That's when you have no normal force with the ground. So yeah, losing contact between two objects means that the normal force they exert on each other is gone. So that's a very good assumption that we can make over here. So when you're here, the only forces acting on you are the force of gravity, and that's it. The normal force here goes to 0, so all you have is the force of gravity pointing straight down. And only a component of that gravity can give you some centripetal acceleration, so let's figure out what that component is. You're also going to have a tangential acceleration, which is actually why you're speeding up in the first place as you go down this hill. But let me go ahead and draw that line over there. So that's going to be just a radius. I want to figure out, I guess, I want to figure out this angle theta. Yeah, I want to figure out this angle theta. You know what? I think I'm going to redraw this. Yeah, let me redraw my hemisphere. So I have that distance r, and I also have that is a distance r. This is r, and this is r. And then I have this, which is h. And I have this angle theta over here. And that angle theta is equal to this angle theta made with the force of gravity. So if I do force of gravity cosine of theta, that will be the component of the gravity force that points towards the center of this hemisphere. That's force of gravity cosine theta. Force gravity cosine of theta. And that would leave this component of the gravity as force of gravity sine theta, which causes the tangential acceleration. I can figure out what theta is because I can do this. I can do my centripetal acceleration is going to be my centripetal force over m, so a centripetal equals force centripetal over m. So a centripetal, which is going to be v squared over r, specifically here it's v final squared over r, equals net force centripetal over m. No normal force at this point. The only force towards or away from the center is force of gravity cosine theta. And then that over m. If I substitute mg in for force of gravity, then the m's cancel and I'm just left with g, so that's equal to g cosine theta. I guess I'll write in the m's and show them canceling out. And v final squared we determined earlier is equal to 2gh, so we can do 2gh over r equals g cosine theta, and the g's also cancel, so it doesn't even matter what planet you're on, or asteroid, or moon, or I guess star, if you can find a way to stand on the surface of a star without burning to a crisp. So cosine theta is equal to 2h over r. Cosine theta is equal to 2h over r. Actually, that gives it away. If cosine theta is equal to 2h over r, then what is this distance? This distance is touching theta. So this distance is equal to, I guess I'll draw it again for more clarity because it is getting crowded over there. I'll draw my hemisphere one more time. If this here is theta, and this here is r, I've got a right triangle over here. Uh-oh. Let me grab that. There. Oh, it was about to fall over again. I need to find a better arrangement to keep my markers from... Oh, I know what I can do. I can just leave them here. Okay, that's perfect. Sometimes I forget how much space I actually have available to me. Anyway, where was I? So, yeah, if this over here is r, and I'm looking at a right triangle over here, I guess I'll highlight that in, I guess in this darker color. I've got a right triangle over here. Then I can see that r is the hypotenuse of that triangle. R times cosine of theta would be this. This is equal to r cosine of theta. And if I multiply the r into cosine theta over here, then I'm left with r cosine theta equals 2h. So r cosine theta is equal to 2h, which leaves, we already defined this as being h. So if r cosine theta is equal to 2h, then r must be equal to 3h. Or no, wait. No, hold on. That's not right. So if r cosine theta is equal to 2h, then... Yeah, if r cosine theta is equal to 2h, then r must be equal to 3h, because this is one full r over here. That is one full r. So if it's composed of h and 2h, then r is equal to 3h. R is equal to 3h. Which leads us to h is equal to r over 3, which we have now proven. Now for the bonus part, what is the angle theta? We can just do a little bit of trig. If r is equal to 3h, then 2h is equal to 3h cosine theta. 2h equals 3h cosine theta. The h's cancel out. cosine theta is equal to 2/3, and if I do inverse cosine of 2/3, inverse cosine 2/3, make sure I'm in degree mode, yes I am, and I'm getting about 48.2 degrees, so you would fall off at 48.2 degrees. Theta equals about 48.2 degrees when you fall off. Alright, so it helped that they gave us the hint that the normal force goes to 0, but hopefully with the explanation I gave about normal force going to 0 meaning objects lose contact with each other and vice versa, hopefully you'll be able to do a problem like this without that hint next time. But I think that is where we will have to end it for today. Hopefully these will prove to be helpful, especially to those of you who stumble upon this before the AP tests this coming week. And yeah, I'm not entirely sure what next week is going to be, which is, I guess, what I tend to say at the end of every one of these sessions now. Probably going to be calculus stuff, but we'll see. I'm thinking of reteaching myself some old math subjects that I haven't done in a while, so I might be starting off with reteaching myself whatever it is I've forgotten from multivariable calculus, so that might be coming soon. Probably the algebra stuff that comes before the calculus in multivariable calculus, so maybe vector stuff and lines and planes. That's what I'm expecting to do next week, but I could end up changing my plans. You never know. Anyway, that'll be it for me. Hopefully this has proven to be helpful, and take care, and I will see you in the next one.